we go. So refining velocity models with time-playing tomography and RTM demigration migrations. So what do we mean by that? Is that the aim of today's presentation is to introduce an efficient and automated velocity model refinement workflows that ensures consistency between the geology and the geophysics. So during the presentation, we're going to focus on two key algorithms, the time-playing tomography in one hand, and then the RTM demigration remigration. These techniques complement each other as it will be demonstrated during the next 20 minutes or so of this presentation. After this presentation that we're going to share with V, we're going to have also a couple of demos to show you as well how it's working with our solutions. But before I go into details about the technology, I just wanted to introduce as well where we stand in the company. So as I'm sure most of you know, the company that we are part of is called Emerson. It's a 140 years old company with 73,000 people globally. And it's a really global leader in automation, technology, and software. So they designed some tools as well, but part of where we are really where, if you see my cursor at the top here, under the AspenTech technology umbrella, which means, that we are really on this software and control tool. And also within AspenTech, we are really basically the subsurface engineering. So we cover all the subsurface engineering tools that you can think about. So what I mean by that is that we have software for processing and imaging, we have software for interpretation, we have software for formation evaluation, geological modeling, reservoir engineering, production modeling, and optimizations. Something worth mentioning as well at this stage is that a lot of those different tools, as I'm referring to now, share the same database. So we share the same, basically, seismic, the wells, the culture files, the grids, etc., etc. We share all this information. So when our customers are using, for example, processing and imaging, if they're using, our tools like ECOS, for example, a time processing tool, then they don't need to get out of the software and re-import that in another software, because everything is linked for P&I interpretation, formation evaluation, and geological modeling. So today's presentation, it's not about all those tools that I was referring to. We're going to concentrate about the bridge between the processing and imaging and the interpretation. So we're going to concentrate on the tools I was referring to at the beginning of this presentation, the time-playing tomography and the RTM tools, which are part of our velocity modeling toolboxes. So we have a few toolboxes within this portfolio, and again, there's a bridge between the P&I world and the interpretation word. And basically within our tool, we have different ways to use different velocity sources. That can be vertical function, velocity time grids, well data, or other kind of sources. Different model type can be used, like model-based, volume-based, or hybrid, and different velocity modeling approach as well. So it can be geostatistical kriging, seismic guiding interpolation, reservoir model, or V0 and KZ minus Z0. We also have what we call the constraint velocity inversion, which is basically a tool which was designed a few years ago now, and we take basically the input vertical functions, but it's not a simple Dix transformation, because we used basically here the extrapolate tender from those vertical functions. So we can do also model updating, of course, Dix-based update, model-based and grid tomography update, and depth conversion as well. And obviously the tools that we are going to concentrate today are those tools which are referred into these red boxes showed on the right corner of your screen here, so that the time-playing tomography and the demigration remigrations. Bear in mind that these techniques are complementary to FWI workflows, so our tools can deliver additional refinement and investigation options alongside FWI. So first of all, before we deep dive into the technology per se, let's talk a little bit about the challenges with traditional approaches. So we have like 5 roughly traditional challenges that we're facing. So the first one is the time depth conversion uncertainties. So errors in the velocity model lead to the mismatch between the seismic dataset and your well markers. And this is shown on the screen. When you look on the right side, you can see indeed an image of the seismic, couple of horizons with a few wells as well, and you can see the markers not being overlaid with the horizons that they're supposed to be overlaid with. So the velocity model that was used for the seismic, obviously, that means it's not correct for the geological data we have extracted for the wells. We also deal with complex and interactive workflows, so it requires repeated migrations, depth updates, and quality checks, often slow and resource intensive. A consistent well mill style, so that's the one I was referring to, so that remains of course well due to imperfect velocity calibrations. Even when we do a few sometime iteration, you can still see some well misstyles. We also have limited accessibilities because typically that's been handled by processing and imaging teams, and it's less accessible to interpreters needing rapid updates. And we have also integrated challenges. So geological and geophysical dataset can remain out of sync, reducing confidence in the interpretations. So what I'm going to show you on the next few slides will be really how to tackle those challenges that we have talked about now. So let's talk first about the time-preserving tomography before talking about the RTM. So the time-preserving tomography, or TPT in short, is set up as a least square problem that considers all the data at once and includes some constraints. In simple terms, it adjusts the model parameters to minimize the difference between the predicted and the observed seismic data while obeying specific rules, the constraints that we're imposing, that ensures the model remains physically and geologically realistic. The assumption that we're making is that the initial model already does a good job of capturing certain aspects of the seismic dataset. What we mean by that is that the velocity model that was used before that, so we have a first velocity model, we have computed a first PSDM, and we of course have output as well, some, let's say, some pre-stack gathers as well. So with this velocity model that we have used to start with, we assume this velocity model is good enough that all my gathers are flat everywhere, right? For whatever depths we are, whatever lateral locations we are. We have already good velocity models. That means that those gathers are flat, okay? So that's very important as an assumption. It also knows the fundamental geological structure present on the reference models. So in other words, while the model is refined to better fit the data, it does not lose the important structure features that were already present. And using this algorithm, you can accomplish several tasks. So depth interpretation, to improve the understanding of the subsurface. We can do a certainty analysis to improve risk assessment, as well as scenario testing. On the few example I'm going to show you this presentation and during the demo, you're going to see actually how this TPT can be used for different kind of scenarios, like depth interpretation, scenario testing, and uncertainty analysis as well. So before I jump to the next slide, I'm going to leave Zvi talking a bit more about the mathematical that is behind tempering tomography. And after Zvi has finished talking about this slide, I'm going to basically take over for the next part. So Zvi, I think it's your time. I think you've seen the screen hopefully.
Okay, thank you, Alan. So yeah, my job is quite easy. It's only one slide, but I hope it tells the big story. So as Alan said, we start with a reference model that is considered a one that is associated or is consistent with the seismic data. That means that at least kinematically, we have no errors. So that's the. But as we know, with all the amount of data that we have, either seismic with all the different configurations and with the geologically constrained and with even other potential fields and so on and so on, still we have still a family of solutions, a big family of solutions that can somehow fit the data within a certain criteria. We call this family of solutions, we normally call them the null space of the inverse problem. So if we look at the on this slide, so on one hand, on the top, we define the TPT as a constrained least square solution, starting with delta M will be the model perturbations, so the model errors, and how the model errors are related to the travel time errors along the waves or the rays. And A is the matrix that is applied on the delta E, making at least within a close or within small errors this relation to be linear. If we take here, for example, the case of transverse isotropy with tilted axis of symmetry, what we call TTI, so the models that the model parameters that we have can be the depth horizons that we have. If we define the model as, let's say, what we call model-based or structural-based representation, or if we can also, we also support here the grid-based representation. And then for the, let's say, the anisotropic velocity parameters, we have the axial velocity. In this case, we only look for the compressional waves. So that's going to be the VP, and there is a hidden assumption that the ratio between the VS and VP is constant. At least for the kinematic case, it's okay. And delta and epsilon of the Thomson parameters, and also what we have are the tilted angle at every point where the actually the velocity becomes it's a vector, and that has also its own direction. So this is the tilt angle is the direction of the symmetry axis of the TTI representation. So in vector notation, delta M contains the delta Z, delta V axial, delta delta, and delta epsilon, for example. If we assume, in this case at least, that the tilted angles, they are reference, and they are not changed in this, they are not going to be changed in this iteration. And delta T rays will be the travel time errors along the two-way reflected rays. But for the time-preserving tomography, this is the beauty, and this is what makes the this procedure actually be very efficient, is that we already say that the model is consistent with the, at least kinematically, with the seismic data, so the travel time errors, delta T, are considered to be 0. So this matrix, which is sometimes we refer as the tomography matrix, or the relation matrix. But finally, at the end, it is a matrix, it's a huge matrix that contain the derivatives of the travel time with respect to the different model parameters. Sometimes or they're normally referred to what is called the Frechet derivatives. So this, the A delta M equal delta T delta equal now 0 can be explicitly represented with the different components of the delta Z, the horizon components, the axial velocity components, the delta component, and the epsilon component. And this is the, let's say, the standard way of looking at the problem. Now, of course, that what we want to have is we want to have the list, or to be able to generate the different scenarios, or I call them legal scenarios, which means that all the scenarios that will be generated should be also consistent with the seismic data. But we don't want all the scenarios, but what we want to have are really the set with what we call the plausible solutions. So solutions that will follow or will be also consistent or controlled by our geological rules or physical rules and so on. So constraining the set of equations, we have I would say the eta is a kind of a positive weight that it's a normalization factor along the diagonal matrix that makes the let's say the solution more stable. We have the damping terms, so we don't want to have very oscillated solutions that are, from our perspective, not physical. And also there is a term that constrain or control the structural smoothing of the operator. And delta M in blue, these are the all parameters in the model that we would like to invert for. So the perturbations of the whole model. The input is marked here by delta M in red, and this is normally a subset, only a subset of the model parameters. So, of course, we cannot modify or perturb all the parameters because in that case, we'll violate the consistency with the data. So this can be, as Alan mentioned, for example, mistized parameters, or can be some velocity perturbations in some of the target layers. Or one very attractive way of doing that, using that, is transforming in a consistent manner isotropic velocity models into, let's say, transfer TTI models. So we move from a scalar, let's say, representation of isotropic velocity into multi-parameters description, but in a sense that the model that we have is still consistent with the data. And when I say with the data, it's not only with the zero offset, it's up to a certain offset or up to a certain subsurface reflection angle. Another thing maybe that I want to say before letting Alan continue is that the computation of the matrix A, or the A transpose A, is, and this is for those of you that have some experience with the seismic inversions, this is a kind of a simulation of the Hessian matrix that we have in there. So this is the heavy part. This is the part that requires either, wave equation solutions. In our case, it's a very dense and massive computation of many rays crossing the whole model. And this is the main part. And this part is computed once. And once we have that, then we'll have all the way to provide the right-hand side, the one that is marked here with red, and then so we impose some perturbations, and then we can get in a very fast manner, actually just applying the matrix on the unknowns, and to get the complete set of the delta M. Okay, I think that I'll stop here, and Alan, you can continue, and I'll be glad at the end maybe to answer some questions.
Perfect. Thank you very much, Zvi. And indeed, as Zvi has mentioned, this is really a more in-depth, basically, knowledge of what TPT is doing exactly. And you're going to hear a lot about the next few slides, exactly what Zvi has said, but perhaps, said a bit differently. So before we look at different examples, I just want also to remind ourselves the differences between the TPT approach and the conventional calibration approaches. So it's a ray tracing approach, and the normal sinus rays are used to update the velocity. For the misstyles, the corrections are made along the normal incidence as opposed to just a vertical stretching, and we account for lateral displacement as opposed just to the vertical stretching. On the right side of the screen, you can see actually what we meant before that a few times by Zvi and myself regarding the state of the pre-stack gathers using those different velocities. So let's say we have a first velocity model, okay, that's what we used to use to compute the first PSDM. And so if we look here, you can see the pre-stack gathers, or one pre-stack gathers extracted from the volume, and you can see indeed it's already a flat gathers, right? So our first velocity model, as we said before, the assumption is that the gathers is already flat. And with the new velocity model being computed, and with the new, PSDM being computed, so this is after TPT, before and after, we have, therefore, if we were to do a new PSDM, which we don't need to, and we're going to talk about that a bit later, but if we were to do a new PSDM with this velocity, we would see that the gathers will remain flat, and of course, the horizons will change a little bit, according to the new velocity models, but the gathers will remain flat. And that's the key importance here, that we preserve the kinematics here of the system. As Zvi has mentioned as well beforehand, what is the most computed intensive is really to compute the ATA matrix. Okay, and this we compute it only once. And after we compute this matrix once, we can then solve this matrix only once. Even if we have, tens or hundreds of scenarios, we just solve it only once. So if we have, let's say, as we're going to see a bit later, if we want to test different velocity update for certain maps, for example, we're going to use that at different constraints. So let's say minus 10% to plus 10%, and we're going to solve it only once. Also, one of the key advantages of this technology is that it's very interactive, very easy to use, so it can be used very easily by interpreters, not only by PNI people, but also by interpreters. And this is referred to what we said beforehand as a bridge technology before the PNI words and the interpretation words. So what do we need for input and output? So input, very easy. We just need the original velocity model that was used to compute the PSDM, the original depth maps as well, and some constraints maps. Those constraints maps, I said by Zvi beforehand, that can be, mistime maps, for example, or that can be, some delta V, delta velocity, isotropic or anisotropic, on some different horizons, okay? So here in the example below, you can see basically what we entered, that was constraints map. So we have input data set here, input velocity model, and then we have as well the mistime maps being shown here. And then after TPT is conducted, we reduce those mistyes here, because the constraint here were the mistyes map. So we reduce those mistyes, and the output that will be generated during TPT will be the new velocity model, and also the depth map associated with this velocity model. Okay, and we can also extract the variation along the updated map, X, Y, and Z. And of course, if you run different, scenarios, it's not only one velocity and one different depth map generated, but different velocity model and different depth map associated to each of those velocity model. So now if we look at actually the example here of how to reconcile the depth redepthing for the interpreters. So as we said before, Zvi or myself, it's a global geophysical approach that corrects the depth misties. So we perform the depth velocity model calibration under the kinematic constraints using this time-varying tomography technology. So as we said a few times now, it's a very easy tool for interpreter or PNI expert as well. And the input necessary is just the velocity volume, seismic horizon index, and well, if we want to reduce those misties. And here's an example where actually we're going to reduce those misties. We have a couple of horizons, the blue one and the yellow one. And you can see here some more markers here extracted from the wells that don't fit to the horizons. And after we do this tempering tomography, we can see now that the new model basically fits with the markers. Not, of course, that as I said before, we generate velocity. We don't generate seismic, okay? The seismic you see here can be automatically generated with RTM. And again, we're going to talk about it about a bit later, okay? Again, TPT, we're just producing new velocity, new depth maps, and later on we can do a PSM if we want, or we can do RTM, demigration, remigration, and again, we're going to talk about it a bit later. Another example that was done here in the Tano Basin, and that was presented a couple of years back at EAGE conference in Madrid. And in the Tano Basin, the subsurface exhibit complex structural and stratigraphic feature alongside significant discrepancies between the seismic dataset and the geological interpretations. So this is what you can see here on the left side. I've got a couple of wells and I have a close-up a bit later to see a bit better. And some of the markers don't fit at all those horizons of interest. So different approaches were tested without any success, but by using the tempering tomography, we were able to reduce those misties. So this is mistime maps of one of those horizons to start with, and you can see later on those mistime maps with the same scale as it is shown on the screen. And this is just a close-up of basically, you can see on the left, couple of horizons, in the red, the orange, and the green, and you can see as well some well markers. And before tempering tomography, you can see 57 meters and 37 meters respectively. And after tempering tomography is applied, we reduce dramatically those misties to 2 meters and 0.5 meters. Not as well that some wells were drilled after this test was done, and the misties were not as big as what would have expected if the work wouldn't have been done. Okay, so we talk about indeed tempering tomography to be used for minimizing misties, but we can also use that for testing scenario, as we said before, also for structural uncertainty assessment, so we can analyze different scenarios and identify model and consistencies based on the different perturbation designs. So this is what we are going to talk about now, actually. If we feed the system with different perturbation maps, what is going to be the output and what else can be done with that? So first of all, we're going to start with a depth image stack, with some depth interpretation done on those stacks, with the velocity obviously used for that. We're going to set up the tomography matrix, add the different perturbations that I'm going to show you a bit later. We're going to QC the results, automatically update the geometric geological model from new displacement. We're going to generate seismic consistent multiple geological models, and that will lead to analysis the impact on GRV and resource estimate. So this is the work that was done on the Volve dataset in the North Sea. The reservoirs is Jurassic and Triassic and consists of thick sands, but is also heavily faulted. And the communication across the faults is quite uncertain, leading to uncertainties in the GRV estimations. Also, note that we have a velocity inversion around the reservoir levels, and this is actually where we're going to fit the different perturbations. So on the top of the reservoir here, these orange horizons here, we're going to have 10 different constraints, and that will be 10 different velocity maps. Okay, so those 10 velocity maps will be the velocity percentages of the maps we have extracted from the regional velocity model. So that will be from plus 15% to minus 15%, and we try so these 10 different maps basically. And what you can see here on the left side, that's the original velocity model with basically the envelope of the results of those 10 different scenarios being run for those two different horizons. So the reservoir here. And you can see as well the faults as well as change as well. And on the right side, you can see with the initial velocity model, with the initial horizon, initial faults as well, and with also the plus 15% variation. And you can see the change of the velocity, of course, as well as the change of the horizons and the change of the fault positioning as well. So as I said, we run those 10 different scenarios in one go. We run that in one go. We don't need to run one by one. And then this can lead later on to GRV estimation as well, based on those results. So to start with, basically the oil in place was estimated to 13 cube meter. And then with a plus 15% velocity uncertainty, this was down to 27% change. So that was quite dramatic. So before I jump into the demo, and I know the time is running, so I'm going to try to keep the time as it should be. But I just wanted to mention the next technology we're going to talk as well, which is the RTM demigration remigrations. So what is this technology? This is a post-stack technology using the RTM algorithm, and it's linked to the results that we have obtained with the tempering tomography. What I mean by that is that we start with the first depth model, the first PSDM that was computed with the first velocity model as well associated with that. And we demigrate, we go to the zero offset time domain. Okay, so using only those post-stack dataset. And then we can remigrate again those post-stack dataset using those different velocity models that was computed using the tempering tomography. And therefore we can obtain some new basically 3D volumes images, seismic volume images that can fit those new velocities as well as those horizons that we have generated beforehand. So again, we don't need to do PSDM. We can, of course, if we want, but we don't need to do PSDM. We can do that because this is quite quick to use and quite efficient to use. Obviously, it depends on the maximum frequency you want to use. And also, the parameterization is quite simple. So it's a very simple tool as well for interpreters to use that. Okay, so I see the time again is running. I've got a few demos I really want to show you before we jump to conclusion and the Q&A session. So for the demo, we're going to look at two quick demos. The first one will be really redepthing. So it'll be really, we have some misties and we want to minimize those misties. So this is the workflow that we're going to do. We're going first of all to look at the current velocity. We're going to generate mistie maps. We're going to store the information into vertical functions that we call the pencils, that are proprietary systems that use to store all the information needed to run the tempering tomography. Therefore, after that, we're going to have a new velocity model, new grids as well, and we can check after that the misties if they are better or not. And we're going also to look at the RTM algorithm during the same demo. And later on, hopefully we'll have time for that. We'll have another demo about a testing scenario. But before that, I'm just going to jump to my other screen to show you actually basically the demonstrations. So hopefully you can all see my screen. So what you should be able to see is here I'm just opening the software, and you see the software, as I said before, is quite large in the sense that we have all those different pieces of software for PNI interpretation, formation evaluation, geological modeling that share all the same database. Okay, so this is basically when I open my software, this is what I see. I see all those software in the same place. All the works that we are going to do next will be linked to what we call the 3D canvas, which is the 3D viewers that we're going to refer quite a few times during these presentations, because this is really when we're going to QC the results using these tools here. And you see what I'm showing you now. Here it's basically the seismic overlay with the velocity, with the few horizons as well I have here, and 3 wells I have here. And I've got, like you can see as well, some misties here as well. So first thing first, what we want to do is generate those mistime maps. So I'm just going here, and basically we can do that very simple here with the tool. I select the first horizon, let's say, and from these first horizons, I just say, compute the mistime grids here, and it will, just show me this mistime grid, which is shown here, and I can just apply here, and it will save those mistime into the system. So obviously I've done that beforehand because I knew it will be, a bit short for time. And basically, these are the mistime maps that we have for the first 3 horizons, okay? These are all the same scales, and you can see the scales here on the right side between -100 and +200 meters. So obviously the idea here is really to minimize those mistyes. So what we are going to do now, we are going to store those informations into what we call pencils, and I'm going to show you just the results here because I don't think we have time to show you how we can generate those pencils, but it's very quick and efficient normally way to run that. But if I open my pencil here, you're going to see that what I've stored in those pencils will be basically the horizons. Okay, so these are my pencil, and as well as basically those perturbations. So the perturbations are stored at each of those horizons here, okay? And again, remember, these are the informations we're going to feed the tomography in order to minimize those maps later on, to have a new velocity model that can minimize those maps here, but is still chemically constrained. So later on, we can just basically build the matrix and then later on solve the matrix. So first things first, we're going to build the matrix, and I'm going simply to select my pencil here. I'm going to select the velocity as well, the input velocity model, and I'm going to select the surface onto which I want to modify the velocity. I want to modify on all of them here. And I can enter a name for my matrix I'm going to generate, and the parameters for the aperture, maximum input offset, etc., etc., as well as for the inversion parameter, if I want to be isotropic only, or if I want to, as Zvi has mentioned, to constrain with some anisotropic model. And then the performance tab as well. And all our tools have the same kind of GUI. So you have the general, all the information, and then the performance tab. You can obviously distribute the workload onto a cluster, and you can also generate some log file, etc., etc. So I'm not going to run the matrix here, but it should take, for this dataset, it should take approximately 1 minute. So it's quite quick to run on the machine I'm using here. So it's not too long, and again, that's quite a powerful tool. And then later we can just solve the matrix. And again, to solve the matrix, we're going to use the matrix that we have stored into the system. So this is the matrix I've used beforehand, and we can later on update the system. So I'm going to tell what constraints I want for my update, and as mentioned by Zvi, some smoothing parameters, sensitivity factor, and also the strength I want to put on those perturbations, those mistime maps, okay? And I can then run the tomography matrix, and I'm not going to do that again here, but bear in mind that will take approximately 30 seconds to run here on this system here. So altogether with the pencils, building matrix and solving the matrix, I would have spent perhaps 3 to 4 minutes if I'm quite large here. So obviously now what I want to see is the results, and I can look at the results here. So I can load the new velocity model that was generated. So that was the model that I generated beforehand. And I can compare this velocity model with the velocity model that I started with. And you can see if I just increase that a little bit. So this was my input, basically seismic, my input velocity model, and my new velocity model being generated, okay? And as I said before, we can also extract automatically the maps from the generation of this workflow. I will just need here to say, extract the grids, okay, extract the new horizons, basically, and I will just select basically my models and update the depth grid. I've done that obviously before, so I'm not going to do that here. And if I show you basically those interpretations, I'm not just going to show you on one example, for example. So if I show you this one here for the second horizons, so this is basically the new horizons. I'm just going to untick this guy for a second. And this is the grid we started with, okay? So you can see the discrepancies between those two different grids. And if I look as well at the velocity, you can see the first velocity and the new velocity. And you can see they fit very well with those horizons. Of course, I can now check the mistime maps, how good they are, which I've already prepared beforehand. And this is the mistime map that we started with. And these are the new computed mistime maps that I have generated just beforehand. And of course, you can see now that we have reduced those mistime maps. We can do a few iterations if we think this is not enough. But obviously, for the sake of this demonstration, I'm just going to stop here there. The last things I wanted to show you is running RTM demigration, remigration. And again, this is all in our tools here in this imaging tomography tab here. And we have this tool here called post-stack RTM demigration, remigrations. So the parameters are quite simple. First thing you will need to select is your input, stack, okay, your input PSDM that was generated with the velocity model that was used accordingly. Okay, and then you can increase the frequency if you want to have a better zero stack, or you can just reduce to 25 Hertz, for example. And then the output volume, you can just enter a name, and that will be basically your demigration. And then I can remigrate using this time the demigrated data set, and then with the velocity file that we have computed with TPT. Okay, and we can generate those two new, basically PSDM. And of course, I've done that beforehand, and I can show you now on the screen. So if I show you the post-stack migration, and basically this is the new PSDM compared to what we started with. So this is what we started with, and this is the new PSDM. And of course, you can see the correlation as well between the grids, the velocity, and all those information. So again, TPT and RTM works well together. Before I finish, I just wanted to show you another quick demo over the next 3 minutes, if possible, and that will be really about testing scenario, because what we've shown you here so far is really about, if I have some mistypes and I want to minimize those mistypes. But as I said before, we can also use that to basically minimize, so testing some different scenarios. It will be exactly the same workflow as what I've shown you before. The only difference is that I can input different constraints into my pencils, okay? And when I solve the matrix, I can solve only once the matrix with generating all those different scenarios. So I'm just going to show you the results here because I'm very constrained about the time here. So these are the velocity and the seismic where we started. So I'm just going to show you that on the screen again on 3D canvas, same tool as what we showed before. And I'm going also to show you basically the different grids, so the different horizons. So this is my velocity here, and the different grids we had. So we had 4 different grids to start with. We had the water bottom, we had the top of the salt, the base of the salt, and the base of the Cretaceous. And the work we have done, it was to impose some constraint on the base of the salt and the base of the Cretaceous. For the base of the salt, we limited to -5 to +5% velocity perturbation. And for the base of the Cretaceous, we done between -10 to +10%. So 4 different scenarios for the base of the Cretaceous and 2 different scenarios for the base of the salt. So altogether, 8 different scenarios. And of course, what I can show you now, the results, will be using the extreme scenario. So between, let's say, -5% velocity for the base of the salt and -10% for the base of Cretaceous, and +5% and +10%. So if we look at the new velocity being generated, and again, this is loaded on the shared memory as I speak, we are going to see basically those new velocity model, and I shall be able as well to overlay that with the new grids as well. So first of all, I'm just going to untick the grid for 1 second. And if I were to look to zoom a little bit perhaps. And if we start with the first velocity model, with the updated with -5% base of the salt, -10% base of Cretaceous, and +5% base of the salt, and +10% base of the Cretaceous. And of course, as I said, I can also overlay that with the new grids that can be generated. So for example, if I overlay that with the new grids for the base of the salt, for example, so I'm just going to hide that for 1 second. And you can see this is the input grid we started with. So that goes hand in hand with my first input velocity model. And now with the first extrema scenario here, I can see indeed if I look at it with this new scenario here. Okay, so this is just what I wanted to show you. I have maybe 1 minute no more for the summary slides that I wanted to show you here. So bear with me 1 second. I'm just going to show you that. Yes, so just for the summary of what Zvi and I have been showing you over the last 40 minutes or 45 minutes, let's say, over the tempering tomography and also the RTM, demigration remigrations. So for the tempering tomography, as you hopefully have seen, it's really a bridge between the P&I world and the intervention worlds, and it works only with post-stack input datasets. So it requires only a velocity model, horizons, and some basic constraints. It's efficient and automatic model refinement. It's faster and more reliable updates to the velocity model compared to traditional approaches. It's maintained consistency between the geology and the geophysics. It improves the structural image, delivers clearer horizons and more accurate fault positioning. We support both isotropic and anisotropic cases, flexible for different geology, and can be used for minimizing misties as well as testing scenario. And last but not least, for the RTM demigration remigrations, we preserve the full wave physics. So unlike ray-based approximations, it is still based on wave equation propagation. So it's keep the RTM quality. We support the anisotropy, work with VTI, TTI isotropic models, which is crucial in modern subsalt and deep water imaging. And it's linked to the tomography, to the TPT we talked about before. So all the new velocity model can be used to feed into the RTM demigration remigration. So you don't need to do another PSDM, you can just do RTM demigration remigration to check your result straight away. And I think we did finish, and of course we'll be more than happy, Zvi and I, to answer any question you should have.